Hi everyone. Today I am going to discuss reactive intermediates. Reactive intermediates means that are short-lived and highly reactive chemical species through which most of the organic reactions occurs are called reactive intermediates. Short-lived means it is 10 power, its lifetime is 10 power minus 6 seconds to just a few seconds. Just a few seconds. This is the life of these reactive intermediates. What is the short life means here? How much its life? 10 power minus 6 seconds. Yes means here seconds to just a few seconds. Means afterwards they are converted into products. In any reaction, organic reaction, reactants are converted into products through intermediates. These intermediates have short life, very less life, and highly reactive. These are the chemical species through which a chemical reaction or organic reaction can occur. Here we have different examples for reactive intermediates. One is carbocation, carbene anion, free radicals, then carbenes, then nitrines, then arynes, otherwise benzenes. So all these we'll discuss one by one in different sessions. Here first I will discuss about carbocations. Carbocations, otherwise called as carbonium, carbonium ions. Carbocations, otherwise carbonium ions. Carbonium ions generally these are formed by heterolytic cleavage. They are formed by heterolytic, not equal. Heterolytic means unequal cleavage. Heterolytic cleavage means among the bonds, otherwise in a given covalent bond, two electrons move with one atom, and other atom will take less electron density. That atom will carry positive charge. Particularly, if that particular atom is carbon, then we can say it is a carbonium ion. For example, here CH3, I am taking Cl. Here two bonds are present. So this carbon, otherwise methyl group, is attached to more electronegative chlorine. So that this chlorine will move from here by taking these two electrons as Cl minus ion. So that here we can get positive charge on carbon atom. So this is a methyl carbonium ion. Similarly, any group. Here I am writing three groups. Maybe hydrogens, maybe R groups, maybe anything. Here this is directly attached to the other group which is having more electronegativity. Here X I am writing. This is a group which has more electronegativity than carbon. So that here these two bonded electrons move along with the X, and X is eliminated as X minus. So that here C bond, here this is the bond, this is the bond, on carbon there will be positive charge. This is called as carbonium ions. In this way, carbonium ions are formed by heterolytic or heterocleavage are written here. We can say it is a heterolytic cleavage. Heterolytic cleavage. Carbonium ions are formed by heterolytic cleavage when carbon is attached to more electronegative atom. We have different carbonium ions are there or carbocations are there. Before going to that different types, first we should know the structure of carbocation. Now we will discuss about structure of carbocations. Here carbon has positive charge. Carbocation means this is the chemical species or reactive intermediate on which it is a reactive intermediate of carbon species. On carbon there will be positive charge and only 6 electrons are present. So this is the reactive carbocation means first here what is carbocation I am giving. Carbocation is nothing but is a chemical species in which carbon carries positive charge and it has only 6 electrons in its valence shell. So what is carbocation? It is a chemical species. Carbocation is nothing but chemical species in which carbon, which is central atom here, carbon carries positive charge. Carbon carries positive charge. Carbon carries a positive charge and only 6 electrons. It is electron deficient. 6 electrons. Only 6 electrons are present. Only 6 electrons are present in its valence shell. Valence shell means outer shell. Otherwise, here in particular molecule around central atom, how many bonds are present? In those bonds, how many electrons are present? We have to count. See here, carbon. Here one group. Here one group. Here one group. Here positive charge. See, this is carbocation. This bond is nothing but 2 electrons. This bond is nothing but 2 electrons. This bond is nothing but 2 electrons. So these all bonds are monovalent bonds. Otherwise, monovalent groups are attached to this carbon atom. So here, how many electrons are present around this? Like this, if you take around this, how many bonds? 3 bonds. 3 bonds means 6 electrons are present. 6 electrons are present and positive charge is present. So 6 electrons, it is not octet. So that we can say it is electron deficient. So always it can accept negative charged species. Negative charged species which are nothing but nucleophiles. Generally on carbocation, nucleophilic attack takes place. That is different in classification of reactions. We will discuss that. So this is the carbocation. Then what is the structure of carbocation here? See here, total how many electrons are present? 6 electrons are present and 3 bonds are present. So all these bonds are sigma bonds only, along with positive charge. Therefore, here first we should know about hybridization. What is the hybridization of carbocation? Hybridization of carbon or carbocation. Carbocation is sp2. sp2. Because only 3 bonds are present. So that the total number of electron pairs, here n value I am writing, n is nothing but what? N is nothing but total number of electron pairs. Total number of electron pairs. So to accommodate these 3 electron pairs, there should be 3 available orbitals are present. The first 3 available orbitals are s and 2p orbitals. So that we have to consider sp2 hybridization. If n value, for this n value is 3. So that we can write sp2 hybridization. If n value is 4, sp3. N value 2, sp. N value is not 1. N value should not be equal to 1. Because the minimum 2 orbitals must be there to form a molecule, otherwise to involve in hybridization, how many? 2 orbitals are required. So n equal to 3 means sp2 hybridization, n equal to 4 means sp3, n equal to 5 means sp3 dehybridization. So there are different types of hybridizations. Among those, carbocation hybridization is sp2, and for sp2 hybridization the shape is trigonal planar. Trigonal planar. Shape is trigonal planar. And here trigonal planar means between these, here I am writing one carbon lies here, positive charged carbon. These 3 bonds are present in this way. Here one group R I am writing, here one more group R, here one more group R. Here between these bond angle should be 120 degrees. What is the bond angle? 120. Trigonal planar, and bond angle is here is 120 degrees. And one vacant orbital also present here. That vacant orbital is present above and below the plane. It is having planar structure, no? So above and below this plane there should be one vacant orbital, because carbon, in this we have total 4 orbitals. One s orbital, 3 p orbitals as per electron configuration. As per electron configuration, 2s2, 2p, 2. Here s orbital lies 3 orbitals. So in excited state, one electron jump from s orbital to p orbital. So 2s1, 2p3. Here 1, 2, 3, 4. So because of positive charge, this orbital is vacated. This orbital, which is pure 2p orbital, which is present above and below the plane, and remaining 3, these are participated in hybridization. These are participated in hybridization. and forms three identical hybrid orbitals 1, 2, 3. So here remaining one is this is pure p orbital, 2p orbital. These are the three sp2 hybrid orbitals. Total how many orbitals are present? 4 orbitals are present. Among these 4 orbitals, 3 orbitals are participated in hybridization. One more orbital is present that is now vacant because of positive charge. That vacant p orbital is present above and below the plane of this molecule. So this is the structure. In this structure, what is the important thing? Important thing is hybridization of carbocation and shape of carbocation and bond angle. So that vacant orbital is present above and below the plane. So this is about structure of carbocations. Then types of carbocations now we'll discuss. We have different types of carbocations we have based on carbon type of carbon. We have different types of carbon atoms. Primary carbon atom, secondary carbon atom, tertiary carbon atom. So there is different carbon atoms we have. So here what are the different types of carbocations? Then stability. Similarly, along with this we have benzene ring related means phenyl carbocations we have and allyl carbocations we have. Different types of carbocations we have. So stability of those carbocations now we'll discuss. Here types of carbocations. Types of carbocations. See, first of all, we should know what is primary, what is secondary, what is tertiary, like carbon atom. See here, here I'm writing one simple example for understanding. Here, see, this is just assume it as a molecule. I'm not adding hydrogen. So this carbon, see, this is the carbon which is directly attached to only one other carbon atom. So that we can say it is primary carbon. And this carbon and this carbon and this carbon and here also one more carbon is there. So all like terminal carbons, these are attached to only one carbon atom. See, this is also attached to one carbon, this is also attached to only one carbon, this is also attached to only one carbon atom. So these all carbon atoms are called as primary. Primary means simply the carbon atom which is directly attached to only one more carbon atom are called primary. If these carbon atoms carries positive charge, we can say it is a primary carbocation. And see here this carbon atom. This is it is surrounded by two other carbon atoms. Otherwise, it is directly attached to two carbon atoms. So that this is secondary. If on this carbon atom positive charge is present means so we can say it is secondary carbocation. Similarly, here adjacent to this carbon if you consider, so it is attached to here one, second, third. So around these three different carbon atoms are there. So that this is tertiary carbon atom. If it carries positive charge, we can say it is tertiary carbocation. So here one, two, three, four primary carbons are there. Primary carbons are there. Here one secondary carbon is there. This one only one secondary carbon is there, and one tertiary carbon is there. This is the second tertiary carbon, and this is the carbon which is attached to four different carbon atoms. That is called as neocarbon. How many neocarbons are there? Only one neocarbon atom is present. So first of all, you should know the types of carbons. Primary, if contain positive charge, it is primary carbocation. Secondary, if contain positive charge, it is secondary carbocation. Like that, tertiary. Then quaternary carbon, otherwise neocarbon is there. But already it has four bonds, so that there is no possibility to get positive charge. So that primary, secondary, tertiary, and methyl carbocation also we can take. Methyl means here only C, hydrogen, hydrogen, and hydrogen. This is having positive charge means this methyl carbocation. This is methyl carbocation. It has no adjacent carbons. So simply we can say it is methyl carbocation. Then here I am writing one more CH3 CH2 plus. This is ethyl carbocation. This is ethyl carbocation because once you observe, positive charged carbon is attached to only one other carbon atom. Then here CH3, then CH, positive charge, here CH3. See this carbon which is having positive charge attached to two other carbon atoms. So that this is secondary carbon, secondary carbocation. Then this carbon here having positive charge around this CH3, here CH3, here CH3. This is this carbon which is having positive charge is attached to three other carbon atoms, so that this is tertiary. This is methyl carbocation. This is primary carbocation. This is secondary carbocation. C plus I am writing. This is tertiary carbocation. So these are the different carbocations here. Along with we have some more carbocations. First, we'll discuss the stability of these carbocations. Stability of these carbocations. So here we have to consider in previous sessions we have discussed about inductive effect, electron displacement effects we have discussed. Among those, inductive effect and hyperconjugation effect we have to consider here, not resonance effect. Resonance effect is only for ring compounds with conjugation, otherwise normal straight line compounds, organic compounds with conjugation only. Means there should be alternate single and double bonds must be there. Otherwise that is not participated in resonance. So here just normal, there is no any pi bond. So that we can consider here one is inductive effect, other one is hyperconjugation effect. Hyperconjugation resonance forms are more means it has more stability. Less number of hyperconjugation means it has less stability. Inductive effect more means it is more stable. Inductive effect less means it is less stable. Why means in not only this carbocation, any intermediate you can take. If it has some charge, it may be positive charge, it may be negative charge. So here these are the positive charged carbocations. So here the formed carbocation, if it is nullified, otherwise decreased due to transfer of electrons towards itself. There is any group which is present adjacent to this, if donates electrons to carbocation, then it will get more and more stability. So positive charge must be compensated. Positive charge must be nullified due to adjacent groups. More decrease in charge, positive charge on carbon atom means it will get more stability. Less decrease in the charge of less decrease in positive charge on carbon atom means it is less stable. No decrease, the positive charge which is formed remains as means it is very unstable. So here you can observe hydrogens. Already in previous classes we have discussed hydrogens have no inductive effect, so that it will not donate these electrons towards carbon, so that there is no any decrease in the positive charge on this carbon atom, so that it is very less stable. It is very less stable. So what we can write here, no inductive effect, no inductive effect here, because adjacent to this only hydrogens are present. Hydrogens have no inductive effect, so that methyl carbocation is very less stable. Then here methyl, here this is ethyl carbocation, primary carbocation, otherwise here I am writing this is ethyl carbocation, ethyl carbocation. In ethyl carbocation you can observe here adjacent to this carbon there is a methyl group. So here we can expect in this plus I effect, plus I effect, and also one more thing is here three alpha hydrogens are present. Alpha hydrogens. See here how many three hydrogens are present. Means here we can write these three hydrogens in this hydrogen, second hydrogen, third hydrogen. Like this we have three alpha hydrogens. So that three no bond resonance, otherwise hyperconjugated resonance forms are present for this ethyl carbocation. So that because of this hyperconjugation, this positive charge is decreased or compensated more compared to this. So that this is more stable than methyl carbocation. Similarly, here two methyl groups are present. So compared to this, compared to primary carbocation, here more plus I effect is there. More plus I and more hyperconjugation. Otherwise, more no bond resonance. No bond resonance depends on alpha hydrogens. Alpha hydrogens means what? So the adjacent carbon atoms to positive charged carbon is nothing but alpha. So this is a positive charged carbon atom. This is adjacent to this. Here also one more. This carbon is alpha carbon. This also alpha carbon. So on alpha carbon, here three hydrogens, here three hydrogens. So that how many total? Six alpha hydrogens are present. Six alpha hydrogens are present. So that here more and more positive charge is compensated compared to this ethyl carbocation. So that this is more stable. Here we can write it as the secondary carbocation, otherwise the isopropyl carbocation, otherwise secondary propyl carbocation. Then this is the next tertiary carbocation. We can say it is tertiary butyl carbocation. In tertiary butyl carbocation, here more and more I'm writing, more and more plus I effect. Why more and more I written here? No plus I effect. Here only one methyl group can donate its electrons, sigma electrons towards itself. Here this arrow mark which I am writing on sigma bond is nothing but inductive effect related. Like this. So here compared to this, here more inductive effect and more and more. Again I am writing more and more, no bond resonance. More and more, no bond resonance again here. No bond resonance. How many? Why more and more are written? Because compared to this, here three hydrogens, here three hydrogens, here three hydrogens. Three alpha carbons are present. On each carbon atom, three alpha hydrogens are present. So that total how many alpha hydrogens are present? Nine alpha hydrogens are present. Nine alpha hydrogens are present. So that here this positive charge is more and more compensated. So that that is more and more stable. So among methyl, primary, secondary and tertiary, which is more stable carbocation means tertiary carbocation is more stable. Why it is so? Why it is so means because of more and more plus A effect. Along with plus A effect, there should be hyperconjugation. Otherwise, no bond resonance. So that this is the order of stability. Examination point of view, they ask like these questions only. Not exactly this question, like these questions they ask. Comparison questions. They give three or four carbocations and they ask which is less stable among those or which is more stable among those. Otherwise, what is the ascending order of stability? Otherwise, what is the descending order of stability? Like that questions they ask. So that this is just for explanation how to study, how to solve the questions. So how to apply the concept I am giving here. So that after completion of this, you have to read as many as questions related to this reactive intermediate stability, so that you can get more concept. Then one more example I am giving, that is with respect to alkyl groups. This is one example. One more example here is methyl carbocation. Here I am writing methyl carbocation, then ethyl carbocation CH3 CH2 plus ethyl carbocation, then propyl carbocation CH3 CH2 CH2 plus, then like this I am increasing one more carbon CH3 CH2 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 plus. This is methyl carbocation, ethyl carbocation, propyl carbocation, then there is butyl carbocation. Among these, which is more stable? Which is more stable and why? Which is more stable and why? Reason is important. So you know, here only we have to consider first hyperconjugation, then after we have to consider resonance. Which one? Inductive effect. So here methyl group no inductive effect. Here there is an inductive effect with respect to this CH3 group and also hyperconjugation. Otherwise no bond resonance. Then here inductive effect and also hyperconjugation both are present. Here inductive effect is present, but hyperconjugation also present. Three hyperconjugation forms and one methyl group can give its sigma electrons to this CH2 plus. Here bigger CH3 CH2 group is present. So that whenever alkyl group length increases, inductive effect increases. Inductive effect is directly proportional to size of alkyl groups in previous classes I given. So here more and more inductive effect. So that see in here and here same hyperconjugate forms, because this is alpha carbon, here this is alpha carbon contain two hydrogens, so two no bond resonance. Here also two no bond resonance. Here three no bond resonance, but here inductive effect is very less because of only very small sized methyl group. So that we can write Lewis order. Methyl group has less stability than ethyl group, then propyl group, then butyl. Butyl is having more and more stability here due to from left to right, from methyl to butyl group, plus I nature, plus I nature increases. Plus I nature increases from methyl group to butyl group. So that here stability of these carbocations increases from methyl group to ethyl group, ethyl carbocation to propyl carbocation to butyl carbocation. Okay, this is about stability of these normal alkyl groups. Next, we'll discuss about allyl and benzyl carbocations. Allyl and benzyl carbocations, different carbocations we have. Allyl carbocation and benzyl carbocation. These are also more stable. These are almost equal stable as that of secondary carbocation among these. Secondary carbocation among these benzyl and allyl carbocations are having more stability. More stability. It is almost equal to secondary carbocation. See, one more example here. Allyl, allyl carbocation, allyl carbocation and benzyl carbocation. Allyl carbocation, benzyl carbocation. Allyl carbocation. Allyl group means what? Here, any group. See here I am writing. For example, CH2X I am writing. This CH2X totally when attached to double bonded carbon, then we can say allyl. This is allyl. This is allyl. We have one more term, vinyl. Vinyl means what? Vinyl is nothing but CH2X. CH2X. So here otherwise this X group is directly attached to double bond. Here CH2X group is directly attached to double bonded carbon, it is allyl. Here X group is directly attached to double bonded carbon atom, then it is vinyl. This is vinyl group and this is allyl group. So here we are discussing about allyl. Benzyl means what? Benzyl means on benzene ring. It is also a type of allyl only. So like this benzene ring. On benzene ring, we can write CH2 plus. CH2 plus. This is benzyl. See here also this carbon has positive charge. So this CH2 positive charge is present on double bonded carbon atom. This is the carbon, double bonded carbon atom. This is benzyl carbocation. If you remove this X from here, here also it will get positive charge. This is allyl carbocation. If you remove this X from here, this carbon gets positive charge. This is the vinyl carbocation. So there are the different types of carbocations. Now here we are discussing about allyl carbocation and benzyl carbocation. Allyl carbocation, see you are writing CH2 double bond CH2 positive charge. This is allyl carbocation. Allyl carbocation has resonance. So because of stability with respect to resonance, it is more stabilized. See here one more resonance form writing here. So this pi electron shifted from here to here. So CH2 plus here single bond CH, a double bond, it is CH2. Like this, it has two direct resonance. It is not no bond resonance. It is directly resonance. Because of resonance, it is more stable. Its stability is almost equal to secondary carbocation. Somewhat less stability than which one? Secondary carbocation. This is allyl. Then we have benzyl. Allyl carbocation is. Then second one is benzyl carbocation. Benzyl carbocation. Benzyl carbocation means here. Place you can write. This is benzyl carbocation, positive charge on this carbon atom. So here this bond shifted here. So we get here double bond CH2, this positive charge is compensated. See, here also positive charge is compensated. Just now what I told, if the formed positive charge on carbon, if compensate, it will get more stability. Here like this it is compensated. So here this bond shifted to here, so it becomes double bond on carbon charge, on carbon positive charge is compensated. And this carbon gets positive charge and here like this. So to compensate this positive charge, it will come here. So here we get one more resonance form. Here double bond CH2, then here newly formed bond after compensation of this positive charge, this carbon now gets positive charge, here bond. Then next this bond shifted from here to here has to compensate this positive charge. So here we get positive charge on this carbon atom. This is newly found bond and here already present bond, double bond CH2. Next step, this bond shifted here to compensate this positive charge. Like this, we have different resonance forms. Different resonance forms. Again here this CH2 gets positive charge here. So because of this resonance, because of resonance, benzyl carbocation also more stable. Here allyl carbocation it is also due to resonance. Due to resonance, it is more stable. So these stability of allyl and benzyl carbocations, stability of allyl and benzyl carbocations have almost stability of allyl and benzyl carbocations is almost equal to secondary carbocation. Secondary carbocation. Stability of allyl and benzyl carbocation almost equal to secondary carbocation. Here we can write stability order for this. Stability order I am writing. So here I am writing order of stability about these three. So first here benzyl, because of more resonance, benzyl carbocation is more stable than secondary. Secondary means CH3, here CH3. This is secondary carbocation. It is more stable than allyl. CH2 double bond CH like this, then CH2 plus. This is the order of stability. Order of stability of these three: benzyl carbocation, secondary carbocation, and allyl carbocation. So what I written, stability of allyl and benzyl carbocations are almost equal to that of secondary carbocation. Means allyl carbocation has somewhat less stability than secondary. Benzyl carbocation has somewhat more stability than secondary carbocation. Here more it is due to presence of more number of resonance. So we have some more examples related to stability of carbocations and some rearrangement reactions. Generally carbocations are participated in rearrangement reactions also. How it is participated in reactions, rearrangement reactions, we will discuss in next session. Thank you. Stay home and stay safe.